Okay, so this is related to some pre-calc stuff. Honestly, I feel like the only thing that makes calculus difficult is pre-calc. So that's where all the troubles stem from, and all the years I've been doing this, that's been the common thread. That people who have difficulty with calculus, it always comes down to issues with pre-calc. Yeah, and so let's see if we can get past some of that. I mean, it's kind of a typo. A little spacing issue here, right? So that's for somebody. So we're going to look at integrals involving trig functions, specifically cases where you have to perform some sort of substitution, some identity substitution related to those trig functions. So we'll start off with the Pythagorean identity, which is sine squared plus cosine squared is equal to 1. And, just very quickly, I mean, I don't want to spend too much time on it because in theory this is something that happened in pre-calc. But just off kind of on the side here, I'm going to draw a circle. With a radius of 1. It's a little 1 there. That circle with a radius of 1, some might call, it's a 1 unit circle, some might call that a unit circle, has some characteristics, but most notably coordinates along the circumference of the circle. So those coordinates are x comma y. All right, x comma y. Now, if I were to decompose that angle that I just created into a right triangle with components corresponding to those coordinates, I would have a distance here of x, that would be this guy here, and a distance here of y, forming a right angle. So that 1 extends from the center all the way out to the circumference. So it's not as relevant anymore, at least not for that part, right? But in a circle, all radii are congruent. So I know that the hypotenuse of this circle has to be equal to 1, all right? So what I get is a Pythagorean relationship. X squared plus y squared is equal to 1. All right, so then you might say, well, okay, cool, that's great. What does that have to do with trig? Well, there's an angle here, a central angle. Right? That central angle extends to the arc, but we call that central angle theta. From that central angle, we get some relationships. For example, the cosine of that angle would be equal to the adjacent side over the hypotenuse. So SOHCAHTOA, adjacent, which is x, over the hypotenuse, which is 1. So that tells us that x is equal to the cosine of theta. We could also get the sine ratio, sine of theta, which is opposite over hypotenuse, y over 1, which tells us that y is equal to the sine of theta. All right, through direct substitution, we can now say that cosine theta as a quantity squared plus sine theta, also as a quantity squared, is equal to 1, which gives us our Pythagorean theorem, cosine squared theta plus sine squared theta is equal to 1. All right, there's not even a little bit of calculus involved in that. That's all pre-calc. But that's where that rule comes from. And a whole lot of other rules are based off of that rule. So if you understand the origin of this rule, then it becomes something that you don't have to memorize. although you might already have it memorized, because most of the time it's kind of right off the tip of the brain when I say, what's sine squared plus cosine squared? You say 1. And it's like, well, why? No idea. My teacher said so. I'm like, cool. That's exactly how we like it. Just regurgitate information, give me the answer that I'm looking for, and then move on. I'd like you to understand it a little bit, right? But what this does is it creates a relationship, a set of relationships, lots of relationships. It tells us that I can replace a cosine squared with an expression involving sine squared. If I manipulate this, if I divide each term by cosine squared, for example, I would get 1 plus tangent squared is equal to secant squared. If I divide each of those two terms, or each of those three terms, by sine squared, I would get cotangent squared plus 1 is equal to cosecant squared. All of that from a circle and a triangle. All right. If you draw the circle and a triangle, you can invent all these rules. Why am I doing this? To torture you, I guess. I don't know. Figurative, good way to kill a few minutes. I could make up different ridiculous reasons. No, the rationale behind it is, yeah, there's rules. They're from pre-calc. If you know them, great. If you don't, this is where they came from. Try to take some time and see if you can understand it, because if you understand where they came from, then it's not something you need to memorize. Right? It's something that'll always be there. All right. What we need to do is be able to use these rules to help us integrate more complicated expressions. All right. Now, I mentioned before that I didn't think that U substitution was in and of itself its own topic. More so, it's a foundation topic for other types of integration. So you'll find yourself throughout all the other techniques that we learn about constantly coming back to the concept of U substitution. And this question is no different, right? Yeah, some helpful guidelines. With the power of cosine or sine is odd, save one factor and convert the others. The idea is that if you have an odd power, you're only one factor away from being an even power, right? So what I would do here is break it up a little bit and write it, instead of cosine cubed, write it as cosine of 5x multiplied by cosine squared of 5x dx. Right, it's equivalent. As long as you keep the argument the same, both of them have to have a 5x. As long as you do that, you're not doing anything illegal. So, at this point, if you're working from the beginning of the course to the end, you'd say, okay, is there a rule? No, we don't have a rule for this. Is there a U that I could select to help me replace one of the factors and then thereby differentiate to allow me to cancel out one of the other factors? Well, derivative of cosine is negative sine. I don't see a sine there. And so that's where the light bulb goes off. You say, well, if only I could make one of the cosines into a sine. Well, you can, because cosine squared x, where are you? Cosine squared x is equal to 1 minus sine squared x. Really, cosine squared of anything is equal to 1 minus sine squared of that same anything. All right, so if it's 5x, it's 5x. If it's smiley face, it's smiley face. It doesn't matter. All right, but what that allows me to do is swap this bad boy out for a 1 minus sine squared of 5x. All right. So then the question becomes, Now can I use U substitution? Is there a U that would allow me to swap out one factor, replace it with a U, and then through the differentiation process allow me to cancel out the other factor? And so, well, yeah, because as long as I have a sine somewhere and a cosine somewhere else, I can at least cancel something. It's just a question of will it be enough. All right. I mentioned this before, when you're dealing with trig functions, a good idea is to take the thing that's being raised to the power. Take the trig function that's being raised to the power. So I'm going to let u equal sine of 5x. If that's the case, through chain rule, du would be equal to 5 cosine 5x dx. All right. Derivative of the outer function multiplied by the derivative on the inner function. All right, so sine becomes cosine of 5x, but then multiplied by the derivative of the 5x, which becomes the 5. All right. Take stock, see what's going on. I can get rid of the sine here, so that's fine. I got an extra 5 I don't want, so let me kill that. 1 over 5 du would be equal to cosine 5x dx. So I got a clean substitution here. I don't know if this is the best way to do it, but I'll just do it like this. That is going to get replaced with this. So we're looking at the antiderivative of 1/5 times 1 minus u squared du. You could distribute through the 1/5 or bring it out. It's up to you. I like bringing it in. Honestly, the only reason I bring it in and distribute it through is because I worry that I'll forget about it later on. So if you're not like that, then you don't need to do that. So anti-differentiate 1/5 u minus 1/15 u cubed plus c. And then it's just a matter of swapping back in the u, which somewhere over here I defined as sine of 5x. Plus c. Infinite space is killing me because I'm losing track of what space I have available. I can bring it in a little bit, I guess. Alright, so the key to everything here is defining your u, but that only happens after you've used an appropriate strategy to break things up. But you look at something like cosine cubed right off the bat, it doesn't necessarily lend itself to a formula. You don't have a rule for that. And then you start thinking in terms of things like u substitution, and before you know it, you're kind of going down a dark path. You don't realize where you're going, when really the solution is right in front of you, and it has to do with pre-calc, not even a complicated Calc 2 approach. Right? So start to really kind of dive into these different processes and say, right, if I have an odd power for a trig function, what is something that I can do? Right? If I have an even power, what's something I can do? But we'll focus on the odd powers for now. Right? Sorry. The second one, you have an odd power. I can do something with that. Right? I also have an even power. You might say, well, I'll replace the sine squared with a 1 minus cosine squared. But you gotta try to at least make the attempt to play it out in your mind. You know, like you don't always have to try to work every solution out in your head before putting pen or pencil to paper, but you should at least consider the situation before you start writing. All right? Then start writing. All right? So if I were to change the sine squared into a 1 minus cosine squared, then everything's in terms of cosine squared. So then you ask yourself, does that improve the situation? Well, u substitution is not going to do me any good because I'm not going to be able to cancel anything. In fact, I'd rather have it be in terms of sine and cosine, basically structured the way it is currently, than actually change the sines over the cosines. But if you're following kind of the letter of the law here, you would say, okay, I see an odd power. So let's save one of those cosines. And then once I do that, I can take this cosine and convert that over to 1 minus sine squared x. All right, so then you stop, take a look, and see what's going on. Is there something else I can do? Well, I can clean it up a little bit, maybe consolidate some terms, but maybe you don't want to. Maybe you say, okay, well, I'm at the point where I know that if I let u equal the sine of x, well, I know sine of x has a derivative that's equal to cosine of x. So let me let u equal the sine of x and see what happens. If it doesn't work, it doesn't work. You try something else. Du would be equal to cosine x dx. You're not wrong at any point if you decide on a u that cancels out all the x's. Right? So if you have an integral that's you're starting off in terms of x's, you decide on a u, you take the derivative, you go through the process, and you do some algebraic hocus pocus, and your new integral, it could be a completely disastrous mess. If it's made up entirely of u rather than x, so there's no x's in there in any way, shape, or form, you didn't do something awful, right? You're on the right track, right? By being able to get rid of all the x's, you did something right. It's just a matter of going from there. And it's usually having more to do with algebra than anything else, all right? And you'll see that in a sec here, all right? Because now I can replace the cosine x dx with a du, and every instance of a sine of x gets replaced with a u. All right, so I'm looking at 1 minus u squared multiplied by u squared multiplied by du. And you might look at that and say, well, how am I supposed to do that? Then you think, wait a minute, work from the beginning of the course to the end. I don't have a rule for it, all right, so it's not that. Let me try something simple, like power rule. If that's the case, I want to clean it up. So u squared minus u to the fourth du. That's power rule, ready to rock and roll. All right, so we're looking at 1/3 u cubed minus 1/5 u to the fifth plus c. And we know u is equal to sine of x. So that must be our antiderivative. But again, the big challenge is getting to that. All right? It's experience. And I'll tell you, when I was a student, I wasn't big on studying. I wasn't big on practice problems. In fact, a teacher got me in 9th grade and said, if you get the assignment after like the first couple of problems, you're good. Maybe try a couple in the beginning, a couple in the end, and you're fine. If you feel like you got it, you got it. And so I made that like a way of life. Try the first couple of problems, I got it. What happens? The first couple of problems are the easy ones. So you go down and sit and take the test. You're like, oh crap, I don't know this. All right. So you start trying to like get away with things initially, but then eventually you settle on your own way of doing things. It wasn't until I got to this material in this course where I was like, you know what, I better do some practice problems. All right. So whether you go to my website in the extra practice section with those worksheets and the answer keys, or if you want to go to the OpenStax textbook, which is linked on my website, to practice some problems in the integration by substitution section. Every lesson in the packet has a little indication right in the beginning of what section it is in the book. So in this one, right there, 3.2. So if you're looking for where to find a particular topic in the OpenStax textbook, it's right in the beginning of the lesson. All right, so if you're ever going to try some extra practice, it's probably going to be related to this kind of stuff. All right, because the biggest challenge with use substitution, aside from knowing that it's a use substitution question, is picking out the appropriate U. Right? Sometimes it's hidden, because in number 2 here, it didn't look immediately like the U would be just the sign of X. You know, in fact, if I were going with it in this form, I would say U is the sign of X. How am I going to cancel cosine cubed with that sign of X? Right? But when you do a little manipulation, you see that that's how it boils down. All right? So a little extra practice goes a long way. All right? So the last thing we're going to talk about before the quiz would be the cases where you have even powers. It's not crazy. There's just more rules. And so for some of us, that may be crazy. It's like, oh, yet another rule. This sucks. Yeah, well, that's one of those things. It's like pre-calc, when I was a student, was the most pointless course that I could ever be sitting in until I was sitting in calculus. And when I realized, oh, that was a pretty important course. But I had the luxury of doing it. I took kind of a non-traditional approach. Did pre-calc and calculus in high school. So I got my learning experience out of the way there. Whereas like I had the aha moment sitting in calculus, man, I should have paid attention in pre-calc. And then when I got to college, I had the philosophy for math and science, you start off taking the lowest level of math that they'll give you college credit for and start from there and just keep going. Right? For me, it never stopped. So 22 math courses later, I maybe built up too much of a head of steam, but it was like, well, they'll give me college credit for pre-calc. It only counted as an elective. It wouldn't count towards my major, but I still took it. And then I was able to really kind of refine my understanding of pre-calc, and then it was off to the races. Now, we're sitting in Calc 2, so what does that mean? It means that ship has sailed. But, you know, if you reflect back upon your time in pre-calc, you either are looking back at somebody who took it seriously and worked really hard, and this stuff is making perfect sense, or you're reflecting back upon a person who is like, oh, what the hell is this stuff for? I'm not even going to pay attention. I'll just wing it on the test, and all this stuff is like black magic, you know? So your biggest review might be pre-calc, not even the calc stuff. All right. So I'll talk to you for a second about where these formulas came from. Not quite the origin story of the Pythagorean identities. I'll actually just start off with a very popular formula from pre-calc, which is cosine of 2x. There's actually 3 variations of this formula, but I'm only going to focus on 2 of them. One of them is 2 cosine squared x minus 1. Right? So what happened here is somebody along the way, and honestly, I think this, before I was talking about this, the integral of secant and how I'm not smart enough to come up with that one. I think this one I'm probably smart enough to come up with. because I would say, all right, I need a rule that's going to allow me to replace a cosine squared with something simpler. All right, and by simpler, I mean something raised to a lower power. All right, this will do it, because if I add 1 to both sides, I get 1 plus cosine 2x equals 2 cosine squared x, and then divide both sides by 2. I get cosine. I get one of those rules that's off the page right now, but you can see it on your pages. 1 plus cosine 2x over 2. But I'll take it a step further. Cosine squared x, I want to write that as actually 1/2 plus 1/2 cosine 2x. If I had a choice between trying to integrate cosine squared x or its equivalent expression of 1/2 plus 1/2 cosine 2x, I'm going with this every single time, because this doesn't even involve complicated u substitution. If I were using u substitution on this, it would only relate to the 2x here. I call that baby u sub, because you could do that on the fly. All right? So there's really nothing to it. But this, you'd be in a spot. Like, what are you going to do with that? There's really nothing you can do. There's no u substitution for just the cosine squared x. But by using a pre-calc substitution, you get it into a form that's actually pretty easy to anti-differentiate. All right? The other variation is cosine 2x is equal to 1 minus 2 sine squared x. All right, so through all the same black magic, what we get is that sine squared x is equal to 1 minus cosine 2x over 2. But again, take it the next step and say instead that sine squared x is equal to 1/2 minus 1/2 cosine 2x. Bless you. So we have a little bit of familiarity here in that, one, they're based off of formulas that we know, but also the two formulas, the two substitutions related to cosine squared and sine squared are not dissimilar from one another too much, because one just has a plus sign and one has a minus sign. All right? So as long as you can keep that straight, you're in good shape. So basically, if you know one, you know the other. So what that does is it allows us to evaluate situations where the power of a sine or cosine function is even, right? Because really, when you're dealing with any kind of even power, it's to the second power multiply. Let's say you had something raised to the 6th power. It's to the second power cubed, but it's always to the second power in some capacity. All right, so I can make my substitution here and replace the sine squared of 3x, so a little bit of an adjustment here, with a 1/2 minus 1/2 cosine, well, it's not going to be 2x, because the relationship here is that if it were x, it would be 2x, but this is 3x, so this should be what? 6x. Yeah, we gotta multiply it by 3. All right. But then for the cosine part of it, it's the same deal, just with a plus sign. So 1/2 plus 1/2 cosine of 6x. So ever so slight adjustment here. All right. So you look at that and say, well, okay, that was so helpful. What did that do? It just, out of the frying pan into the fire. It just made the situation a bazillion times worse. But we have conjugates here, right? Two binomials, one with a minus sign, one with a plus sign. When you distribute it out, and you're like, distribute this out, it's going to be a nightmare. But the outer and inner terms are going to cancel. That's what happens when you multiply conjugates. All right, if I were to use the FOIL process, the first values multiply to give me a quarter. The outer values would give me positive 1/4 cosine 6x, but then the inner ones would give me negative 1/4 cosine 6x. Cancels out. So then I just multiply the last values. 1/4 cosine squared 6x. Minus cosine squared 6x. All right, so again, you might look at it and say, situation has not improved. But I would disagree with that, because here we had both sine and cosine raised to the second power, so we had a fourth degree equation here. All right, so the power, the degree of an equation or an expression is related to the highest power that makes up that expression. All right, so you multiply the two factors together, you're going to add the exponents, you're going to get a power of 4. But here I'm getting a power of 2. So I just reduced the power of this by a factor of 2, which is great. I just got to go a little bit further, because I still have a cosine raised to the second power. So let me apply this substitution a second time. So I'm going to have 1/4 minus 1/4 times, what am I going to replace cosine squared 6x with? Yeah, 1/2 plus 1/2 cosine 12x. So a little distributive property. I mean, you have to do some math. But the idea is that you can do the math now. It's doable. Before it wasn't. All right, so we're going to have the antiderivative of 1/4 minus 1/8 minus 1/8 cosine 12x dx. You can combine some terms. All right, so we're looking at 1/8, because it's 2/8 minus 1/8, minus 1/8 cosine 12x dx. And then we're pretty much there. We just actually, I mean, you look at this and say, well, what do you mean we're pretty much there? We still have to anti-differentiate. All we've been doing is a substitution in algebra and cleaning it up. If you do all the substitution, algebra, and cleaning up, then the antiderivative part should become easy. All right, when we did the u substitution, we selected the proper u. We put all the values in. We cleaned it up. We simplified. When you actually got to the part where you had to find an antiderivative, it was nothing. Increase the exponent by 1, divide by the new exponent. Right? Here it's a little bit different, but it's still not going to be that bad. All right? We do all of this so that this becomes easy. All right? Now you could use u substitution here, but I mentioned before that what I like to call baby u substitution is the way to go. All right? Now the 1/8, that first 1/8, that's a constant. That's going to anti-differentiate to 1/8 x. All right? We'll take care of the other part here in a sec. So what you're going to do, whenever your trig function is only off by a constant multiple, you really don't have to do u substitution. You could define u as u equals 12x and go through the whole process. That's perfectly fine. There's nothing wrong with that. You just do the work on the side, you squeeze it in, and it's perfectly fine. And you know, on a test, I might even consider doing it that way, only because I don't want to take a chance of screwing something up. But what you could do is say, all right, well, I know that the antiderivative of cosine in general is equal to sine. All right, so I'm just going to pop that there. All right, now it's not sine of x, it's sine of 12x. So I'll put a 12x there. And then you kind of play the what if game. All right, you'd say, all right, well, what if this were the antiderivative? Right? I mean, I could just leave it like that. It would be ridiculous because I don't have a plus c, I don't have a sign in between. But let's just say that I thought that this was the antiderivative. I would check it by taking its derivative, right? When I do that, I would get cosine of 12x times 12. All right, so that's a problem. I don't want a 12. I want it to be negative. And I need there to be a 1/8. All right, so all I did was I built the coefficient into what I needed it to be in order to correct for what I was going to get when I took the derivative. So I made the assumption that, well, it had to involve a sine of 12x, all right? The derivative of sine x is 12 cosine 12x. Well, I don't want the 12, so that goes in the denominator. I need the negative 1/8, so that comes in, and there you have it, all right? So you're just building the coefficients. Now, if you don't like that, and you don't have to like it, because my brain works in mysterious ways, so it's not for everyone, but if you do like it, go for it. If you don't like it, then use substitutions there for you. It's a little bit more work. And it's not even a lot more work. I call it baby U substitution, baby U sub, because it's not like a lengthy U substitution approach. If you were to do it out, it'd be a couple of steps, right? But you could do it on the fly. So the way we can avoid baby U sub is to do U sub on the fly, which is basically the autocorrect as you go on, right, through the process. But I leave it up to you, right? You can't go wrong if you use one of those two strategies. All right, so I'm going to put a star on number 4. I like to do my stars in red. I don't know why I did it in purple there. A little simpler in the setup for number 4, but it's got the same kind of intricacies as number 3. So you're gonna need to take some time.